Welcome to the lecture series on superconducting resonators. In this video, we demonstrate how to design a resonator quantum chip using Qiskit Metal. This series is brought to you by the NYU Nanolab, the laboratory for quantum materials and devices. We would also like to give special thanks to the Nord Tech Hub and the Microelectronics Commons for making this lecture series possible. As the goal of this presentation, you will learn how to go through the process of designing a quantum resonator chip using Qiskit Metal. With this workflow, we can set design parameters, generate resonators of varying lengths, and define couplings to a central feedline. The resulting design can then be exported as a GDS file for fabrication or simulated to evaluate resonance frequencies, coupling strengths, and quality factors. We begin by introducing the Qiskit Metal library, setting up a design, and in the end, a step-by-step guide to create resonators, launchpads, and connections. In the next session, we will connect these design steps to electromagnetic simulation using ANSYS HFSS to perform eigenmode and impedance scatter simulations to determine the modes of resonance frequency and finding the scatter parameters of our microwave chip. Also, you will learn how to export the design in GDS to proceed with fabrication steps. Qiskit Metal is an open-source Python framework developed by IBM for designing superconducting quantum chips. It provides a flexible way to create layouts of resonators, qubits, and other circuit elements, all defined through Python code rather than manual CAD work. Once a design is built, Qiskit Metal can export the layout to standard formats like GDS for fabrication, or send the geometry directly to electromagnetic solvers for simulation of resonance frequencies and coupling. This makes it especially useful for researchers who want to iterate quickly between design, simulation, and experiment. For installing Qiskit Metal library, the full source code and installation instructions are available on its official GitHub repository, github.com/qiskit-community/qiskit-metal. Time to jump into some coding. Let's start developing a design in Python environment. In this tutorial, we are using Visual Studio Code Compiler as an environment to run Qiskit Metal. Any other compiler would also work. For more details, reach out to Qiskit Metal's GitHub repository. In these videos, we won't be covering the installation section of Qiskit Metal. Please make sure it's already installed on your computer. Otherwise, watching the rest will feel a bit like trying to make popcorn without a microwave. To begin working with Qiskit Metal, we first import the package and initialize a planar design workspace. This creates the environment where we can build and simulate our quantum circuit layouts. By importing Qiskit_Metal, it launches the GUI, which provides a visual interface for designing and managing our components. Next, we define the design by creating an instance of Design Planar, which sets up the 2D layout environment for our circuit. We then pass this design to Metal GUI, which launches the graphical interface, where we can visually add, edit, and inspect components on the chip. In this step, we configure the physical dimensions and environment of the chip. By enabling overwrite_enabled, we allow modifications to the design parameters. We then set the chip size in the X, Y, and Z directions and define the distances to the sample holder above and below, representing the vacuum spacing. These settings are crucial for accurate electromagnetic simulations. For more advanced designs, multiple layers can be defined to support multi-layer quantum chips. By running this block, we can see an overview of the dimensions defined earlier. Now we import the launchpad wire bond-driven class from Qiskit Metal's component library. This class is used to create launchpads, which are essential for delivering microwave signals to and from the quantum chip and are usually placed at the edges of the design. Here, we define the first launchpad by instantiating the launchpad wire bond-driven class. Since we aim to place launchpads on opposite sides of a 5x5mm chip, we will create two instances, port 1 and port 2. Each parameter defines a specific geometric or electrical aspect of the launchpad. POS_X and POS_Y set the location of the launchpad on the chip. Orientation defines the rotation angle of the pad in degrees. Pad_width, width of the wire bond contact area. Pad_height, length of that same wire bond area. Pad_gap. Distance between the launch pad and the surrounding ground plane, important for impedance matching. Trace_width and trace_gap. Define the width and separation of the tapered transmission line section. Lead_length. Length of the narrow trace section leading into the circuit. Taper_height. Controls how gradually the pad tapers into the trace. Larger values result in longer tapers. This triangular transition shape ensures better impedance matching and signal integrity between the pad and the microwave transmission line. To reflect the newly added launch pad in the GUI, we use GUI.rebuild. This command refreshes the layout view, ensuring that all recent changes are properly displayed in the graphical interface. After rebuilding the GUI, running GUI.autoscale automatically adjusts the view to fit all visible components within the window. This is helpful after adding new elements, ensuring the entire layout is centered and fully visible without manual zooming or panning. Here, we import the root straight class from Qiskit Metal's transmission line library. This class allows us to draw a straight coplanar waveguide between two components. We create a straight coplanar waveguide connection between the two launch pads by instantiating the route straight class. HFSS_wired_bonds equals true ensures that wire bond connections are modeled in HFSS simulations. Pin_inputs specifies the start and end points of the route. Here the route starts from the tie pin of port 1 and ends at the tie pin of port 2. Trace_width and trace_gap. Define the conductor width and the spacing to the ground plane, which together determine the CPW impedance, matching to 50 ohm. This step completes the main transmission line on the chip, connecting both ports with a straight transmission line. Here, we import the coupled line T class, which will be used to create the coupling section between each resonator and the main feed line. This component defines where the resonator connects to the feed line and controls the coupling strength through its geometry. In this design, the coupled line T will form the input side of each resonator. The output side will later be set as an open circuit termination, ensuring that the resonator reflects signals at its designed frequency. Together, these elements define the start and end points of each resonator structure. Here, we create the coupling section for the first resonator using the coupled line T class. POS_X and POS_Y. Set the position of the middle point of the coupler relative to the chip's origin. Orientation defines the rotation of the coupler, in this case, facing 180 degrees to connect properly to the feed line. Coupling_length. Length of the parallel coupling region between the feed line and the resonator. Down_length. Vertical extension from the coupling region before the resonator starts. Fillet, rounding radius for the corner of coupling side, improving fabrication quality and reducing current crowding. Coupling_space, gap between the coupler and the feed line which directly influences coupling strength and quality factor. Open_termination equals true, ensures the far end of the resonator is left open, creating the reflective boundary needed for resonance in this half-wavelength design. Finally, we run GUI.rebuild to refresh the layout and GUI.autoscale to fit the new component into the view. And here is the coupled line. Now to the next library. We import the guided_wavelength function from Qiskit Metal's CPW calculations module. This tool is essential for determining the effective wavelength of signals traveling through a coplanar waveguide, which differs from the free space wavelength due to the substrate's dielectric properties and the coplanar waveguide's geometry. By providing the operating frequency, trace width, gap, substrate height, and film thickness, guided_wavelength calculates lambda g, the guided wavelength in the CPW. ETFS QRT, the square root of the effective relative permittivity. Q, a geometry factor used in CPW analysis. These results are critical for accurately sizing resonators, ensuring they resonate at the intended frequency once fabricated. This find_resonator_length function computes the physical length of a resonator using the guided wavelength in a coplanar waveguide with the latest design parameters. Frequency, operating frequency in Hz. Line_width, CPW center conductor width. Line_gap, CPW gap between center conductor and ground plane. N, 2 for half wavelength resonators, 4 for quarter wavelength resonators. Substrate_thickness equals 350 micrometers, substrate height. Film_thickness equals 200 nanometers, metal layer thickness. In its process, first it calls guided_wavelength to get lambda g, HFSS QRT, Q. Then it divides lambda g by n to get the resonator length for half wavelength or quarter wavelength designs. Finally, it converts the result to millimeters and returns it as a string. By using the define function and giving the desired values, we can extract the length of the resonator we are designing. We use 6 micrometers for the center width, 10 micrometers for the gap to the ground plane, substrate thickness of 350 micrometers, and film thickness of 200 nanometers. Also, don't forget to determine the half or quarter mode of the design. Here, we will design a half wavelength resonator. So 12.14 millimeters would be the total length of our resonator. Keep in mind that many other factors could also come into play when simulating the design, and this value would not necessarily be the final correct number. But it gives a good initial guess. Now let's go back to the design. Here we import the open-to-ground class from Qiskit Metal's terminations library. This component is used to create an open-circuited stub that is referenced to ground. In superconducting resonator design, an open termination acts as a reflective boundary, ensuring that the standing wave pattern is correctly established inside the resonator. By combining open to ground with a coupler, like coupled line T that we designed earlier, we can define the complete geometry of a half wavelength resonator, including its coupling to the feedline and its reflective end. Open_end variable will be the open end of the design using open to ground component. Here are the list of variables. POS_x and POS_y set the position of the open end relative to the chip's coordinate system. Orientation equals 90 rotates the termination so it aligns with the resonator's geometry. Termination_gap, the gap between the resonator end and the ground plane which influences the end's capacitance. Gap and width, define the CPW dimensions at the termination, keeping them consistent with the resonator's line. Finally, GUI.rebuild refreshes the layout, and GUI.autoscale zooms to fit the new component into view. We can see the open end now. The open end will appear as a hovering object, which is somehow not a resonator, right? Soon, a meander-shaped line will connect the coupler and the open end together. Time for the main body of the resonator. Here, we import the route meander class from Qiskit Metal's transmission line library. This class is used to draw a CPW with a meandering path, rather than a straight line. This is especially useful for resonators where the physical length must be longer than the available straight space on the chip. Since our chip is limited to 6.25 by 6.25 millimeters, we can't fit a straight line of 12 millimeters to it. By introducing controlled bends, the meander allows the resonator to achieve the desired electrical length while fitting within a compact chip layout. In this step, we create the meandered resonator using the route meander class. Initially, since we don't yet know the exact values for every parameter, other than the connection pins and the total electrical length, certain choices could lead to errors in the layout or unexpected geometry. To avoid this, we start with initial numbers just to visualize the basic shape and ensure the component is placed correctly. The variables are pin_inputs, define the start and end pins of the meander. Here are the coupler's end and the open termination. Lead. Set straight CPW segments before and after the meander. Both start_straight and end_straight are 0 here. Spacing. Gap between adjacent meander traces. 100 micrometers here. Asymmetry. Shifts the meander with respect to the center of the meander so it aligns with the terminals. For now, it is 0 since we don't know our needs. HFSS_wire_bonds equals true enables modeling of wire bonds in HFSS simulations. Total_length. Electrical length of the resonator, 12 millimeters here, as we found earlier. Keep in mind that Qiskit automatically includes the coupling section's length in the total value, so no adjustment is needed. Trace_width and trace_gap. CPW conductor width and gap, kept consistent with the rest of the design for proper impedance. Fillet. Corner rounding radius, which reduces current crowding and improves fabrication yield. 100 micrometers is the value here. Finally, we run GUI.rebuild to refresh the design and GUI.autoscale to fit the new resonator into view, letting us visually confirm that the geometry and placement look as intended before fine-tuning the parameters. This shape is everything other than a beautiful curved meander. Let's see why. When we first run the code, the meander is generated, but with an error in its geometry. This happens because the fillet value, which is 100 micrometers, is set equal to the spacing between the lines, again 100 micrometers. In practice, this leaves no clearance for smooth turns, so the meander path overlaps or distorts at the bends. To correct this, we need to reduce the fillet radius to a smaller number. This keeps the corners rounded, but ensures the bends fit comfortably inside without collision. The fillet value is changed to something more reasonable, like 40 micrometers. After making this adjustment and rerunning the code, the resonator rebuilds with properly shaped meanders, giving a cleaner layout in the GUI and ensuring that the design can be fabricated reliably. Now that the meander is generating properly, the corners still appear too sharp and not well balanced across the structure. This issue is linked to the base alignment of the meander, which is controlled by the parameter asymmetry. The asymmetry variable shifts the meander path along the axis parallel to the meander lines, in this case the x-axis. By changing its value, we can push the meander left or right to avoid sharp kinks and create smoother, more uniform curves. For this example, the asymmetry value of 200 micrometers gives a corrected version of the final shape. This value could be optimized by fine-tuning the design and trying different values. And here it is. The shape looks to be okay and is giving no errors. The design could be optimized further if you try different values in different situations. For example, increasing the spacing from 100 micrometers to 150 micrometers reduces mutual coupling between meander lines, improving isolation, even though the footprint becomes slightly larger. This shows how small parameter adjustments let us move from a correct baseline design to an optimized one. In a case of putting a wrong element in the design, it is possible to remove the element by delete_component command. This block shows how to remove components from the design. By giving the name of the component to the command, you can remove and redefine the component in the GUI. And we are done. The design is ready to be exported and simulated. Let's recap what we learned. In this tutorial, we learned how to launch Qiskit Metal, start putting components for a simple resonator readout chip, and properly edit and optimize the design. This tutorial will give a better understanding for the next session to how properly simulate and extract the microwave parameters of the design using ANSYS HFSS. In addition, Qiskit Metal allows us to extract the design to the GDS file format, which gives us the ability to manually edit and customize the extracted design and proceed with the fabrication steps. The GDS extraction will also be covered in the next set of presentations. Thanks for your attention.